Welcome back, everybody. Um, in this lecture, we're going to talk about rotational energy and momentum. Um, 2 lectures ago, we introduced the concept of solid body rotation, and we talked about um, rotational kinematics, how to describe rotation in terms of a rotational velocity, a rotational or an angular acceleration. Um, we related those quantities to linear velocity and linear acceleration. We talked about the rolling without slipping condition. In the last lecture, we talked about torque, which is forces which cause changes in a solid object's rotational state. We came up with a rotational analog to Newton's second law, which included rotational inertia, or moment of inertia, as it is sometimes called. And today we're going to talk about energy and momentum. So we're going to take the concepts we've been building of conservation laws and see if we can apply them in the context of rotating objects. So the first thing we have to talk about is how to define rotational energy, or energy of rotation. So we're going to go back to the same very simple rotating solid object that we talked about when we derived the moment of inertia, which is our stiff rod, which has no mass but keeps our heavy object here, our ball, at the end of the stiff rod at a fixed distance from the axis of rotation. So the rod will rotate as the mass sort of orbits around wherever this fixed axis here is. So the linear kinetic energy of our moving object will just be 1/2 mv squared, and we have essentially a turning without slipping condition, or in this case just the tangential velocity is related to the angular velocity by r omega. So we can replace our we can replace the velocity here with the square of r omega, so that our kinetic energy is 1/2 m r omega squared. And we can take the r squared part of this and combine it with the m, and notice that this here, mr squared, is the rotational inertia, or the moment of inertia. And so we can recover a form for kinetic energy that looks very similar to linear kinetic energy. It is an inertia times a speed squared. In this case, the inertia is rotational inertia, and the speed squared here is angular velocity squared. But we again have recovered something that has the same form of its linear counterpart, but uses angular quantities instead of the linear quantities. And so we could do things like, for instance, ask about or compare the translational kinetic energy of a rolling sphere to its rotational kinetic energy. All right, so a solid uniform density sphere has a moment of inertia, or a rotational inertia here, given as 2/5 mr squared. And again, we could make these. We'll make these capital here. There's no particular need to make them lowercase or uppercase, but we'll make them capital here because that's what it says over on the screen. These you can build up with sort of volume integration and the like. On exams, we're likely to just give you what's the moment of inertia of this object. And we know that the translational kinetic energy, which I'm going to call K sub t here, that's 1/2 m times speed squared, and that the rotational kinetic energy, K sub r, is 1/2 I omega squared. So the question is, how do we relate these two? Well, the first thing we can do is plug in the rotational inertia. So this is 1/2 times 2/5 m r squared times omega squared. And the 2/5, or the 1/2 and the 2 cancel, and that gives us 1/5 m r squared omega squared is the rotational kinetic energy. And then again, we can apply the rolling without slipping condition to rewrite this in terms of velocity. So that the rotational velocity is 1/5 mv squared, and the rotational kinetic energy is 1/5 mv squared, and the translational kinetic energy is 1/2 mv squared. Obviously, the translational kinetic energy is larger, but not hugely so than the rotational kinetic energy. The cat wants out. All right, well, let's try another one. This one says, a string is wrapped several times around the rim of a small hoop with a radius of 8 centimeters and a mass of 0.18 kilograms. The free end of the string is held in place and the hoop is released from rest. After the hoop has descended 75 centimeters, calculate the angular speed of the rotating hoop and the speed of its center. So the only force here acting on our object is gravity. Gravity is a conservative force, and so energy is going to be conserved in this condition. So we could do our usual trick. We'll draw ourselves a picture. So there's our hoop, and it's attached to a string which is wrapped around it several times. Our hoop has a radius of 0.08 meters and is released from rest. So at moment 1, it's not moving. It is, however, at some higher point than it will later be down here. We can draw it again. There it is again, same 0.08 meters. And the distance it has traveled there is our 75 centimeters, or 0.75 meters. And now down here at moment 2, it's got some speed, some velocity v that it's moving at, and also therefore, let's see, it must be rolling this way. So it's got a angular velocity going around like so. So energy is conserved. We can say that the energy at moment 1 equals the energy at moment 2. And at moment 1, it doesn't have any translational kinetic energy because it's not moving. It doesn't have any rotational kinetic energy because it's not turning. But what it does have is gravitational potential energy. So we'll write that down, m times g times this height here. And at moment 2, it has, well, we've gotten rid of the gravitational potential energy down here, but now it has both linear translational kinetic energy and rotational kinetic energy. So down here it has a 1/2 mv squared, the translational kinetic energy, plus 1/2 I omega squared, the rotational kinetic energy. And for a loop, the moment of inertia is just mr squared, because again, all of the mass of this loop is at the same distance from the rotation axis. So we can plug that back in to our kinetic energy equation. So equals 1/2 mv squared plus 1/2 mr squared omega squared. And now we can apply a rolling without slipping condition, that V is R omega. And we can decide which one we want to apply it in. We can either replace V over here with R omega, or we can replace the R squared omega squared with a V squared. In this case, it's asking us to find the angular speed first. So let's go ahead and get rid of the linear velocity. So 1/2 m r omega squared plus 1/2 m r squared omega squared. And indeed, those are, we applied this here. And so we can write down here that mgh is equal to, well, these are the same, so that's just m r squared omega squared. The masses cancel, and we're left with omega squared is equal to gh over r squared, or that omega is therefore the square root of gh over r. So that's the square root of 9.8 meters per second squared times RH, which is 0.75 meters, divided by our radius, 0.08 meters. So that's 9.8 times 0.75. Take the square root of that, divide by 0.8 or 0.08, and we get an angular speed or an angular velocity of 33.9 radians per second. And then it asks us how fast is the center of the hoop moving, and so we can use again our rolling without slipping condition, that V is R omega, and that's 0.08 meters times 33.9 radians per second. And that gives us a velocity, a linear velocity of 2.71 meters per second. Where again, here the radians, we write it in, but radians are essentially a unitless quantity. And so meters times radians per second is going to give us the units of meters per second. And we'll do one further one here. Says, Indiana Jones has set a trap while pillaging, set off a trap probably. Yes, set off a trap while pillaging an archaeological site. A 20,000 kilogram spherical boulder 2 meters in diameter is rolling without slipping down a ramp at him. If the boulder started from rest at the top of the ramp 3 meters above the floor, how fast is it moving when it reaches the floor? All right. So here we have a ramp, a great big boulder up here, which has a radius or a diameter of 2 meters. And a height here of 3 meters above the floor. And here's poor Indiana Jones, you know, with his fedora hat. and his whip. He's running this way, and the boulder is going to come chasing him down like so. Nothing's sliding, there's no friction at work, so basically this is another energy conservation problem. So moment one, moment two, when the ball when the sphere gets to the bottom of the hill. So we can say the energy at moment one equals the energy at moment two. And again, in this case, at moment one, what we've got is gravitational potential energy, mgh. And at moment two, we've got kinetic energy in the form of translational kinetic energy plus rotational kinetic energy. For a solid sphere here, we've got a moment of inertia of 2/5 mr squared. And so we can put that over here. So this is 1/2 mv squared plus 1/2 times 2/5 mr squared omega squared equals mgh. The 2's will cancel, the masses will cancel, and so we've got gh over here is 1/2 v squared there plus 1/5 r squared omega squared. And we're going to turn that r omega into a velocity by using the rolling without slipping condition. So now we're going to get rid of, instead of getting rid of the velocity, we're going to get rid of r squared and omega squared. So this is 1/2 v squared plus 1/5 v squared. And indeed, this is 7/10 v squared. And we're solving for velocity, so speed squared is then 10/7 gh, so that our speed is the square root of 10/7 gh. So that's the square root of 10 times 9.8 meters per second squared times 3 meters all over 7. So 10 times 9.8 times 3 divided by 7. Take the square root of that, and we get a speed here of 6.48 meters per second. So Indy better be running pretty fast if he's going to outrun that boulder, because 6.5 meters per second, that's fairly swift, at least for ground travel on foot. All right, next we'll do a slightly more complicated example that will remind us of some other things that we have learned during the semester. So this one says, the pulley has a radius r and a moment of inertia I. The rope does not slip over the pulley, so we have a turning without slipping condition. And the pulley spins on a frictionless axle. The coefficient of kinetic friction between block A and the table is mu sub k. The system is released from rest and block B descends. Block A has a mass ma and block B has a mass mb. Calculate the speed of block B as a function of the distance d that it has descended. All right, so in this case, we do have friction at work, at least friction between the table and block A. And so we can't use energy conservation, but we can use the work energy theorem, which says that the work going from, that the work being done here is the change in the energy, or energy 2 minus energy 1, where we've got box A here sitting on a table connected via a pulley. Go around the pulley, and here's our box B. All right, so that's our initial condition, our moment 1. And then at some time later, box B has descended some distance. So now box B is down here. It's descended some distance here, D. We still go back up. The pulley is still up here. Now box A is closer to the edge of the table by, again, that same distance, D. It's moved. But now also, box A is moving at some speed V, and box B must also be moving at that same speed V, and the pulley, well, the rope is going around the pulley here at some speed V, and so the pulley must have an angular velocity omega that is commensurate with that speed. So, there are several pieces of this that we're going to have to put together. We're going to have to write down the energy at moment 2, the energy at moment 1, and also a formula for the amount of work being done in terms of distance and kinetic friction coefficient and so on. So let's start with work here. We'll draw ourselves a free body diagram of box A. There's a downward force, ma times gravity. There's an upward force of the normal force from the table, and then there is a kinetic friction force to the left. The upward and downward forces on box A have to be in equilibrium because the box isn't accelerating up or down. And so the normal force minus ma times g must be 0, which just means that the normal force, or the magnitude of the normal force, is just ma times g. Which means that the magnitude of our friction force, F sub k here, which is mu k times the normal force, is also just mu k times ma times g. And since the work then is going to be minus fk times d, because the force is that direction, but the displacement is that direction, so that's minus mu k times ma times g times the distance d that the box moves. So that's the amount of energy that friction is removing from our system. The energy at moment 1 is just, well, it's no kinetic energy, no rotational kinetic energy, no kinetic energy, so it's just the gravitational potential energy, and we'll use this as our gravitational potential energy as 0 point. So it's just mb times g times d at moment 1. But at moment 2, well, we've lost our gravitational potential energy and we've converted it into kinetic energy, but it's kinetic energy here, here, and there. So we have kinetic energy of box B, but we also have the kinetic energy of box A, and the rotational kinetic energy of our pulley. And the pulley has a rolling without, or a turning without slipping condition, so V equals R omega, or omega equals V over R. And so this term over here, we'll just rewrite the rest of this. This is 1/2. They're both 1/2 V squared. We're going to have MA and MB in the middle. So this is MA plus MB times V squared. So we've combined those first two terms into a single term, plus now 1/2 I times V squared over R squared, where we've replaced omega here with V over R. Everything here is multiplied by V squared, so we could write this also as 1/2 times MA plus MB plus I over R squared times speed squared. All right, so now we can put everything together. We can go back to our work energy equation and say that work, well, the work is minus mu k times ma times g times d. That's the work. You know what, actually, I'm just going to give this a little bit more room. So the work here is minus mu k times ma times g times d. So this is work equals E2 minus E1. E2 is 1/2 MA plus MB plus I over R squared V squared, and E1 minus MBGD. And we've been asked to calculate speed. So we're looking for velocity. We're looking to solve for V here. So let's move this term over to the left. So that's MB times G times D minus mu K times MA times G times D is equal to 1/2 MA plus MB plus I over R squared V squared. Both of these first two terms are have a GD in them, so we could pull that out. So that's GD times MB minus mu K MA is 1/2 MA plus MB plus I over R squared V squared. Multiply the 2 over on both sides, so we can move that 2 over there, and then divide by this big inertia term. So 2GD MB minus mu K MA divided by this big old inertia term MA plus MB plus I over R squared is our V squared, and thus our velocity is the square root of that great big thing. 2GD M sub B minus mu sub K M sub A over M sub A plus M sub B plus I over R squared. Take the square root of that. It's a big old ugly algebraic equation, if we'd had any numbers for this problem, we could have plugged in some numbers and simplified our algebra a little bit. But the basic principle here is that we have a work energy problem, and again, it's just a matter of being pedantic. Let's lay out both of the diagrams and keep track of literally all the moving parts here. So we have an energy of altitude, of gravitational potential energy. We have 3 versions of kinetic energy over here, and then we also had to calculate the work lost through friction with the table. Right, so all of those are pieces that we've built up over the semester, but as we get here into the late part of the semester, we're able to model more and more complicated problems that take into account more and more effects, right? So we originally would have done this problem with just forces. Indeed, probably to begin with, even as a frictionless table, and then we would add friction. Then we used energy and the work energy theorem, and now we were able to add rotational kinetic energy to add yet one more piece of realism, basically, to our model for this system. All right, well, so we've talked about rotational energy. We've used rotational energy in 2 or 3 examples. Energy also has a rate at which it can be delivered or removed from a rotating object, and so that would be rotational power. First, we could talk about work being done by rotation. So if you've got again, our object over here at the end of a long massless rod here, there's a force dotted into a ds here. So that's the work being done. We could write that in terms of this angle phi, as opposed to the usual, which would be this angle here. So the cosine term between our force and our displacement is 90 minus phi. And the cosine of 90 minus phi is just the sine of phi. Okay. So this is f ds sine phi, and that in turn can be written as, well, that we have the relationship between ds and d theta is the usual one, that ds is r d theta, and therefore we could write our work as f times r times sine of theta d theta. That fr sine theta term is just the torque, so the work is just torque times d theta, or again, sort of f dot ds, except now it's in all rotational quantities. It's our rotational force, torque, and our rotational displacement, d theta. If the torque isn't constant as you're moving around, then you can turn this into an integral. And the power is just the rate at which work is being delivered, rotational work is being done, so it's the time derivative of torque times d theta, and we can turn that into torque times the time derivative of theta dt, which is torque times angular velocity. And this looks a lot like power equals force times linear velocity that we ran into. This is the rotational analog of that. And this can be used, for instance, when you're talking about electric motors or motors of any kind, and you want to talk about the power being delivered to spinning motors. That power is often in the form of a rotational power. So for instance, here it says, an electric motor consumes 9 kilojoules of electrical energy in 1 minute if 1/3 of this energy goes into heat and other forms of internal energy in the motor. So of the 9 kilojoules, we're actually going to get 6. Let's do this in black, not blue. We're going to get 6 kilojoules of useful work out of it in a time delta t of 1 minute or 60 seconds. Then the power being done here, the power being delivered here is work over delta t. So 6 kilojoules, that's 6,000 joules in 60 seconds. Well, that's 100 joules per second, or 100 watts of power. And power is also torque times angular velocity, and we're looking for torque, so we can then say that torque is power divided by angular velocity. So that's our 100 watts of power and our 2,500 RPMs. Well, RPMs aren't a SI unit, so we need to convert that. 2,500 revolutions per minute, and there's 2 pi radians per revolution, and 1 minute is 60 seconds. So that's 2,500 times 2 times pi divided by 60 is about 262 radians per second. And so our torque here is 100 watts over 262 radians per second, or about 0.38 Newton meters. That would be the torque delivered by this motor. Okay, so we've talked about energy considerations. We've done some energy conservation problems with rotation. We've done some work energy problems with rotation. We just did a power problem with rotation. We have also been talking about momentum, which is another conserved quantity, or another quantity that is conserved under certain conditions. And the question is, well, is there a rotational analog for momentum? And the answer is, of course, yes, there is. Linear momentum, if we went back, remember, linear momentum we could get by rewriting Newton's laws, or Newton's second law, F equals ma, and combining the mass and the velocity into a new quantity of momentum that says that the force is the rate of change of momentum. So to make another analog for this equation, then we would need to replace force with its rotational equivalent, torque, and a new quantity, angular momentum. And then we would hope that the torque would be the rate of change of angular momentum. So what does this angular momentum quantity have to look like then? Well, the definition of torque is that it is R crossed with F, right? So that was the definition of how we got torque, by applying a force at some distance r from the rotational axis, and we can replace F with its momentum equivalent, that F is the rate of change of the linear momentum. Now, there's a product rule that we can apply for the multiplication when taking a derivative here. which is basically just like the product rule for normal multiplication, right? So the derivative of u crossed with v, that's the derivative of u crossed with v plus u crossed with the derivative of v. The only change is that we have to keep the order of u and v the same because cross products order matters. All right, and so the whole reason for doing this is that the second term here, r crossed with dp dt, looks like the second term you would get if you tried to take the time derivative of a quantity r cross p. And this first term here, dr dt, is 0. Or sorry, drdt cross p is 0 because drdt, well, that's velocity, and velocity and momentum are in the same direction, and the cross product of two vectors that point in the same direction is 0. So the first term is 0. So this r cross delta p, or dp dt, this r cross with the time rate of change of momentum, is also the time derivative of the quantity r cross p. So this being equal to torque, that means that r cross p is a good candidate for being our angular momentum. So this is again just working through what I sort of laid out, that r cross dp dt times dr dt cross with p, that would be the time derivative of r cross with p. But dr dt and p are pointing in the same direction, and therefore the cross product of that first term is 0. And so we can call this quantity r cross p angular momentum, and then we have returned to a version of Newton's second law in terms of torque being the time rate of change of angular momentum. So this angular momentum is another vector quantity. Like all the vector quantities, there's a right-hand rule associated with its direction. So again, if we have our spinning plate like so, it's got a rotational velocity going like so, and its rotational velocity vector is in that direction. Well, the angular momentum vector is also given by that same right-hand rule. And remember, we could write down often that momentum was mv, and the rotational equivalent of that would be that angular momentum is linear inertia. This is linear inertia times speed. Well, this is angular momentum is angular inertia times angular speed. And indeed, from the definition of torque as I times angular acceleration, and also as dl dt, then you can work through the algebra, and indeed this linear or angular momentum is angular inertia times angular velocity, works just like linear momentum is linear inertia times linear velocity. If there are multiple torques, then you sum them up as usual. If there isn't any external torque on a system, then your angular momentum is conserved. And in particular, if there isn't any external torque on your system, but there are internal torques or internal motions to a particular system, then the total angular momentum of that system is still conserved. And this gives us problems that behave in very much the same way that momentum conservation problems and collisions and the like behaved in linear momentum, but they come out in terms of angular quantities. So again, with energies and momenta, there is this pattern that we can find a rotational analog to each of the usual things. There's a rotational analog to kinetic energy. It's over here. There's a rotational analog to momentum, and it looks the same with just angular quantities put into it. There's a relationship between momentum and force, which is mirrored by the relationship between angular momentum and torque. This sort of one-to-one similarity or echoing of the linear motion equations in the angular motion equations kind of allows you to, if you can remember these, you should probably be able to pick or to figure out those, although obviously these will also be on the equation sheets. All right, well, let's see if we can put this linear momentum, this angular momentum into practice here. Here's a relatively straightforward one. It says an ice skater goes into a spin with her arms extended. She then brings her arms in close to her torso. So she's going from having her arms way, way, way out. You can't see that, but her arms are spread out, and then she brings her arms in, and as she does so, she's bringing mass in closer to her rotation axis, and so she's changing her moment of inertia by doing so. So there aren't any torques at work here, so momentum before is going to equal momentum after, and we can write that down as moment of inertia at moment 1 times omega moment 1 is moment of inertia at moment 2 times omega at moment 2. And then the speed at which she's rotating afterwards is just then I1 over I2 times the speed at which she was rotating beforehand. Since she's pulling her arms in, remember mr squared is the general form for rotational inertias. If you're making the r's smaller, then you're decreasing your rotational inertia. So I2 here is going to be less than I1 when she pulls her arms in, which means that I1 over I2 is going to be bigger than 1, so that in other words, omega 2 then must be greater than omega 1. So she's going to speed up as she pulls her arms in. Question is, has her rotational kinetic energy changed? Well, let's find out. 1/2 I2 omega 2 squared, how does that compare to 1/2 I1 omega 1 squared? Well, the I2 is smaller than I1, but omega 2 is bigger than omega 1. So it's a numerical question. Those are going, the I2s goes down, but the omegas go up. Which one wins? Well, we could rewrite this as 1/2 I2 omega 2 times omega 2, and we could rewrite this one over here as 1/2 I1 omega 1 times omega 1, and this is L2, and that is L1. That's angular momentum of 2 and the angular momentum at 1. So this is 1/2 L2 omega 2 versus 1/2 L1 omega 1. And now the rotational inertia, or the rotational momentum, the angular momentum of both of these is the same, L2 equals L1, but omega 2 is greater than omega 1, so kinetic energy of rotation 2 is bigger than the kinetic energy of rotation 1. So she has more rotational kinetic energy having brought her arms in, and that means that her energy has changed, which means that she did work somehow. How did that happen? Well, she has to pull her arm in towards her spinning body as it spins. And doing so, she has to exert an inward directed force with her arm muscles. and move the arm in an inward directed direction. So force times a distance does positive work. As she pulls her arms in, she's doing positive work, and that shows up in the rotational kinetic energy of her spinning. Let's try a little bit more quantitative problem here. So, a playground merry-go-round with a mass of 135 kilograms and a radius of 1.4 meters is rotating with a frequency of 0.52 revolutions per second. What's the magnitude of its angular velocity in radians per second after a 27 kilogram child gets onto it by grabbing its outer edge? The child is initially at rest. So we're going to model the merry-go-round as a uniform disk, and this is essentially an angular collision problem. We have our spinning object, right, that comes into contact with a stationary object, and then afterwards we have the spinning object and the formerly stationary object rotating together. This is the rotational equivalent of a perfect inelastic collision problems. Two objects come in, one object goes out. So let's see what we can make of this. The mass of our disk here is 135 kilograms. The radius of our disk here is 1.4 meters. And our initial velocity, our initial angular velocity is 0.52 revolutions per second, which we're going to convert into 2 pi radians per revolution. And so that's 0.52 times 2 times pi. That's 3.27 radians per second is our initial rotational velocity. Our initial rotational inertia, well, there's the inertia of the disk, right, which is 1/2 m of the disk times the radius of the disk squared. So that's 1/2 times 135 kilograms times 1.4 meters squared. So 1.4 squared times 135 times 0.5 gives us 132.3 kilogram meters squared. And after the collision, after the kid jumps on, we have that same 132.5 or 0.3 kilograms. We have the original rotational inertia, but plus we have the mass of the child times the radius of the disk squared, because the kid jumps right onto the outside edge. So that's our, again, 132.3 kilogram meters squared plus 27 kilograms at a distance of 1.4 meters squared. .4 squared times 27 and plus our previous answer, and that gives us a total rotational inertia afterwards of 185.2 kilogram meters squared. And the momentum before is the momentum afterwards. So I before, omega before equals I after omega after. And thus omega final is just omega initial times the ratio of the two moments of inertia. So that's 3.27 radians per second times our 132.3 kilogram meters squared over 185.2 kilogram meters squared, and that gives us an angular velocity of 2.34 radians per second. So again, the math. This is the equivalent of when we have a perfect inelastic collision, and the mass afterwards is the combined mass of the rotation or of the inertia of your two colliding objects. In this case, it's the combined rotational inertia of our disk and the child. But this is works very much like a collision problem, and there's a number of these kinds of things where you can basically apply momentum conservation and use momentum conservation, write it down in the momentum before, the momentum afterwards. Again, we're using angular quantities as opposed to linear quantities, but the method for solving these things is very similar to the methods we were using for momentum. All right, we'll do one final example. Another one of these rotational momentum problems. It says here, 3 children are riding on the edge of a merry-go-round that has a disk of mass 92 kilograms, a radius of 1.7 meters, and is spinning at 18 RPMs. The children have masses of 20.4 kilograms, 26.4 kilograms, and 31.8 kilograms. If the child who has a mass of 26.4 kilograms moves to the center of the merry-go-round, what is the new magnitude of the angular velocity in RPM? So again, 1/2 mr squared for a uniform disk. So I don't know about you, but when I was a kid, this was the way we did things. You'd get everybody, you'd spin the merry-go-round up as fast as you could, and everybody would be hanging on the edge, and then you'd get usually the biggest of the kids you'd convince them to crawl their way to the center of the spinning merry-go-round, and it's just like the ice skater bringing her arms in. What you're doing there is lowering the angular inertia, lowering the moment of inertia, and so but keeping the angular momentum. And so conservation of angular momentum means that as you lower the moment of inertia, you speed up the velocity, and the merry-go-round would speed up, and everybody would get squished to the outside, and it was great fun. And then somebody would fly off the merry-go-round, go flying through the air and smash into something. And I can't imagine why merry-go-rounds are harder to find on playgrounds anymore. All right, well, let's model this fun phenomenon here. We're going to do a before and an after picture. So beforehand, we have, here is our merry-go-round with 3 kids on it. I'm going to go ahead and label them A, B, and C. And the merry-go-round has a rotational velocity omega 1. The mass of our disk is 92 kilograms. The radius of our disk here is 1.7 meters. And the initial rotational velocity is 18 RPM. And mass A is 20.4 kilograms. Mass B here is 26.4 kilograms. And mass C is 31.8 kilograms. So that's sort of the before picture. And the after picture, well, which one? The 26 points, so B went away. We still have A and C. Now we're going at some velocity omega 2. and B has moved to the middle. And so the rotational inertia will have changed. So the rotational inertia of the disk is 1/2 mass of the disk times r of the disk squared. And the inertias of A, B, and C, rotational inertia of A is ma rd squared, and rotational inertia of B is mb times the radius of the disk squared, and rotational inertia of C is the mass c times radius of the disk squared. And the rotational inertia at moment 1 is just going to be the disk plus A plus B plus C. But the rotational inertia at moment 2, well, we're going to still have the disk, we're going to still have A, and we're going to still have C, but now B is now mass of B times 0, because you're right at the axis of rotation, and so that B term went away. So if angular momentum is conserved, that L1 equals L2, that means that I1 omega 1 equals I2 omega 2, and thus that omega 2 is just omega 1 times the ratio of the moments of inertia before and afterwards. So that's ID plus IA plus IB plus IC on the top, and I disk plus IA plus IC on the bottom, with no B term on the bottom. So again, we can just start plugging those in. The disk, these terms all have an mr squared in them. The disk has a 1/2. So we're just going to have, this is going to be mass of the disk over 2 plus mass A plus mass B plus mass C times r squared on the top, and mass of the disk over 2 plus mass A plus mass C r disk squared on the bottom. And the disk terms cancel, the r terms cancel each other out. And so this is 92 over 2 plus 20.4 plus 26.4 plus 31.8 on the top. And on the bottom, the same 92 over 2 plus 20.4 plus 31.8 times omega 1. So 92 divided by 2 plus 20.4 plus 26.4 plus 31.8. That's 124.6 on the top. And on the bottom, 92 divided by 2 plus 20.4 plus 31.8 is 98.2 kilograms on the bottom, times omega 1. So omega 2 is our, that turns out, let's see, 124.6 divided by 98.2 is 1.27 times our 18 RPM, gives us a final answer of 22.8 RPM. So by having one of the children work their way to the center and work their way to the center, that child will have to do work pushing in towards the center of the rotating disc, and that work will come out as increased rotational energy as the disc spins faster. All right, that's all for this time. Next time we're going to look at our final subject for the semester, which is revisiting equilibrium in the context of things that can now rotate as well. Until next time.